Alright, today we're looking at mechanical heat recovery with ventilation, okay, an MHRV or MVHR, whatever you're calling it, right? This question is from the 2013 exam paper. It's the question 10, it's passive house, right? There's always a passive house question on the paper. Um, so, mechanical heat recovery is one of those ones that kind of comes up, or you can bring it into a couple of different questions, okay? So the question says it's proposed to install an MHRV system in a passive house as shown in the drawing. Draw a single line diagram of the given room layout and indicate a preferred location for the unit. Show a typical design layout for the ducting to the unit and indicate clear the direction of airflow in all the ducts. Describe how an MHRV, mechanical heat recovery ventilation system, works. Right? Okay, so firstly, before we do that, we're going to have a look here at, I suppose, firstly, what is a mechanical ventilation with heat recovery, right? In new builds, obviously air tightness is one of the most important things. You know, we don't want any air leaking out. Obviously, that would cause problems. I mean, it's energy inefficient, and you're losing heat that you're gaining, whether that be from some sort of a heating system or from solar gain or whatever you've got. You spend all that money to put in the insulation in the house. Why would you leave it leak out through gaps and things like that? So that's why a lot of money is spent on air tightness. Now, when you have a house airtight, that I suppose brings along its own problems that need to be solved. We breathe out CO2. There's a lot of more moisture in the air when the air isn't being changed, and that brings along things like mold growth, and over time fungus will build up, and there'll be spores in the air, and that is bad for your health. So when you don't have enough of an air change, that is a problem. So we'll read this here first. Mechanical ventilation with heat recovery is an alternative to natural ventilation. Natural ventilation in a passive house isn't really an option. This system does not rely on the weather, so it's more reliable. It uses ductwork to direct the air around the dwelling. Okay, so pipes the air out as well as the air in. As the air is directed around the house, it passes through a central unit where the heat is exchanged, which heats the incoming fresh air using the outgoing warm stale air, right? We'll skip down there. Because there is ducting to each room, vents to the outside of the building are not necessary. This is important, okay? There is no unwanted air escaping. This makes the building more airtight, which reduces the energy costs. The air change per hour, the ACH, can also be controlled. Now, you'll be looking to get your ACH there to around 0.6 air changes per hour. There are some companies out there that will, if you look up their websites there, they'll say to you that they can get it up to 1.2, 1.5. But 0.6 there would be a kind of a standard air change per hour. But the thing about these MVHR systems is that you can control the air change per hour. So if you want more air coming in, you can turn it up. Obviously that will have a knock-on effect on your electricity bill, but look, it's still handy that you can control it on this system. The elimination of the vents in the windows and the walls means that there's less risk of condensation and mold growth. Cold drafts are eliminated and pollutants are effectively removed from the rooms. Okay, so I'm going to scroll down here and I'm going to get a diagram, right? You might have seen this diagram in the book already. The control unit is usually placed in the attic of the dwelling, right? Okay, that's in a two-story house, really. In a modern build, if you were building your bungalow or something like that, maybe a dormer, you might decide, you know what, I'm going to put in a big utility. You've already got noise in the utility from your washing machine, your dryer, whatever you have inside there. This is basically a utility anyway. So, I mean, you could put that inside there and keep your living spaces away from it, such as your sitting room, your lounge area, or your bedrooms, I suppose. You can see here, I'll scroll over with the cursor there, you can see here on the right hand side, this is the air exchange unit. On the top left, you can see the fresh air coming in from the outside. Now, in the summer, the air from the outside is warm, so nothing needs to happen, and it goes straight through the heat exchanger and it doesn't mix with the stale air coming from the inside, but the heat is taken from the air from the inside and it's used to heat that air coming in from the outside. So you have fresh air, fresh cold air coming in, goes through the box here, and you have fresh heated air coming into the inside, going into the rooms that will need it. Now, that's in the summer. In the winter, when the air is much colder outside and the air comes in, goes into your box, and it's preheated then in the winter time before it mixes, or not mixes is the wrong word to use there, before it's heated from this air that's coming out from the inside. So that fresh air needs to be preheated before it gets heated again from this recovery unit, and then the same thing is piped in there. You can see here some of the extract regions, right? So your kitchen is an obvious one, your bathroom another obvious one. You have a shower, you're doing wash up, you're cooking, whatever you're doing inside in your kitchen. You can see that there's pipes with the air being sucked up into that unit, and it goes into our heat transfer unit and circulating pump up here. Now look, that will create kind of a vacuum, not a vacuum is too strong a word to use, but that will create a difference in pressure between this room and the next room. So that will in turn pull air through or underneath gaps in the doors from the other room. So for example, there is no pipe going out of the living room, but the old air is going to be sucked out of it all the same, and will be sucked into the kitchen and then up into your exchange unit. At the same time, there is air being pumped into, we'll say, your living room or your bedroom or livable space or whatever it is, and that's been pumped in there, but that's the fresh heated air that's been pumped in there. Okay, so it's very, very important there that you can see that diagram there and maybe take a sketch of that there later. Okay, so I'm going to go back to that question there now, and I'm going to say here, so it's proposed to install a mechanical heat recovery with ventilation system in the house shown. Show a typical design layout for the ducting to the MHRV unit and indicate clearly the direction of airflow in all the ducts. Right, so we've looked at a diagram there a second ago, and we're going to pick where we're going to extract our stale air from. Now, if I was answering this question, I would be saying this is a definite, this is our kitchen area. You're cooking in here, you're washing up, there's hot water, there's people in there, it's a room that a lot of people will be using throughout the day. Therefore, that will need to be an extract zone. The same goes for your utility and for your bathroom, which is here in the corner, right? These two zones here, I would say, absolutely need to be extract zone. Every other zone other than that then, so your lounge, your entrance, bedroom, and the dining area, they can be supply zones. Okay, now you have to have clearly labelled this diagram. You don't need to put in furniture or anything like that. So draw the rooms and we use red or something and blue. So red for extracting out to the unit, and then blue for bringing back into the rooms that need the supply. It also says indicate a preferred location for the MHRV unit. Now in the book it said, where I just showed you there, it said to put it up in the attic, but if I'm looking here at this utility, I can see clearly here that there's a space there, right? There's a space there in that corner that I would see would be ideal for putting this unit. Now, if you want to make an argument for putting it in the attic, by all means do that. But as I said already, this is a utility. You may as well have it with the rest of the utilities. Is it going to be loud enough that it's having an impact on your sleep? Well, the bedroom is at the other side of the house. The dining room also the other side of the house, and there's a concrete wall plus a bathroom in between these two, or this room. Okay, so I don't think it's going to have too much of an impact. Okay, plus you're also keeping it quite close to your extract zones, and you're also close to other utilities, and might make it easier for access to later when you're cleaning out when you're cleaning it out and servicing it. Okay, so I'm going to click in here. There's an answer here. You can see here, this is what I was describing: a red zone or a pink zone where the unit is placed in this corner here, and you've also got access to the outside here. I mean, you can see this arrow here where the air is coming in, and then you've got an exhaust where the air is going out. So I suppose that's something to consider as well. Go back to the question. Describe how a mechanical heat recovery ventilation system works. Okay, I think we've kind of gone through that already, but we'll scroll down here and see what the department has to say about it. It ensures that the internal temperature of the home is maintained at 20 degrees all year round. Okay, that's fine. That's a very comfortable temperature to be at. Moist warm air is extracted from the kitchen, bathroom and utility and drawn through a filter in the MHRV unit. At the same time, outdoor air is drawn through a separate filter. Okay, this outdoor air passes through a fine filter to ensure dust, pollen and other contaminants are removed. This provides better air quality than simply opening a window, because obviously your window will not filter any of that stuff. That makes sense? Teams, go away. In the MHRV unit, the extract air and the outdoor air do not mix. Now this is extremely important. Instead, they pass through heat exchange unit. If they were to mix, you would have stale air coming back into the house. Right? That would be contaminated air. You do not want that. Okay, this heat exchanger unit is made up of a number of very thin metal or plastic plates, and the heat in the extract air heats one side of each plate, okay? And then that hot plate then will heat the air as it's coming in. The outdoor air is now warm and filtered and is now called supply air. The supply air is pumped into the living spaces and the supply zones, right? It's actually a fairly simple a simple system. Okay, well it's not that simple, but it's a simple in theory, using the heat that's already in the house. Okay, go back to the question. Discuss in detail 2 design considerations that should be taken into account when deciding a preferred location. Okay, so as I said, I've chosen that area there. Couple of reasons. I mean, there's the sound, and there's a reason there. You don't want to be hearing this thing. You could be talking between 25 to 30 decibels, which is, in relative terms, it's low enough noise level. It's a fan that's spinning, so you will hear it. But if you keep it away to the side of the house here, it will seem like it's just some other utility. Okay, it will not have an impact on your sleeping, as it's the other side of the building. Again, for servicing, easy access. You're here to the back door. Be able to get at the fans from the front, or the filters from the front. Very, very easy to change those then. Whereas if you were up in an attic, for example, you have to make sure that you have styro or something like that in place, and easier access. Okay, so we'll go back in here. Also, I suppose another thing to consider is I have it in or close to the extract zone. That will shorten the distance of the ducting that's necessary. The shorter the distance of the ducting that's necessary, the more effective and less energy that will be wasted. Okay, so it's important that when we're trying to be energy efficient, that we're not wasting energy. This will run on electricity, and you don't want to be wasting more electricity to drive that air all around the place and then suck all that air out. Okay, so shorter spans of ducting will also add to our energy efficiency. So we'll scroll down here and we'll see 2 design considerations for the location of the MHRV. Energy conservation, okay, that was the one I was talking about just there. Should be located within the thermal envelope of the dwelling. This reduces the likelihood of heat loss through the supplier air ducting. So the longer the span of the ducting, the more chance you had to lose air or lose energy through the ducting itself. Second one here, the unit should be located as to minimize the length of ducting. Supply and extract rooms should be grouped. For example, in the house shown in part B, the extract rooms are grouped together. Okay, so we talked about that already. Maintenance, mentioned that. The unit should be located in accessible area to facilitate routine maintenance. For example, the filters and the outdoor air filter would typically need to be replaced annually, right? In cities where the air quality is poor, the filters may need to be replaced every few months, okay? That just depends on where you live. The noise, mentioned that as well. The MHRV should be located where the noise generated by the fans will not cause a disturbance. As I said, inside in the utility, it's already there with more noisy utilities. So, I don't think it's going to cause much of a problem inside there. Whereas if you were to put it up in the attic in the centre of the house, although the ducting would be shorter, you would possibly risk the fact that it's going to be closer to your bedroom or something like that, which may not suit because the noise again. Also, you would be lengthening the distance to ducting to the external wall for extract air and feed air, we'll call it. In cities where air quality filters may need to be replaced every few months. Okay, I read that already. The passive house standard requires that the sound produced by the MHRV unit does not exceed 25 decibels. Right, 25 decibels is not that high. It wouldn't be too much higher. It would be around the same go as your washing machine or something like that. The MHRV unit is an appliance like a washing machine or tumble dryer. It may be preferable to locate in a utility room or within a cabinet in the kitchen. Okay, so aesthetics, I think that's probably one of the least acceptable answers out of the four there. Okay, look, it is an acceptable answer because obviously you have to live in your home and you have to, if you walk out and you see this big unit, you don't want to hit the side of it. But these first three would be the ones I'd be concentrating on here. Okay, thanks very much, lads.